Hello. It's my pleasure to introduce our next speaker, who I usually used to see on other side of the screen, Van Leer. She will talk about minimal unital cyclics, infinity algebras, infinities as subgroup, and the real homotopy types of closed manifolds.
Yes. Okay, so thank you. Actually, in the announcement, there also rational homotopy type, but I forgot a rational is the title here, but it is included in the my talk because here's a Here's a plan of my talk. That is a model of a rational homotopy theory and the real homotopy theory. Then that is kind of very quick overview to see that. Then I introduce some new relatively new notion of the Hodge homotopy and minimal unital cyclic infinity algebra. Then I say that how to use this notion, and another core notion I should introduce in the my talk, that the isotopy modulo to have the classification of my real and rational. So I forgot again here rational, homotopy type of closed manifold. And then I say that use the technique introduced is Fiorenza-Kawai-Lê-Schwachhöfer and Kawai. You can reprove some reason previously proved by using Sullivan theorem and look very hard. So that's even one of my co-authors try to find counter example because cannot understand the proof. Yeah. So quickly there possibly there are mindful model of the rational homotopy, but the most popular is Sullivan. Sullivan, how to say? So replace, say that's a losum. Replace a topological space is commutative differential gradient algebra. And then if the rational homotopy type, then you consider piece-line smooth form, and the real homotopy type we consider smooth form. Yeah. And then Sullivan model, he has this kind of free space, so that's a commutative different graded algebra. So that is the free extent. What is the information? Information is only differential. Differential, therefore, differential encode everything, but the most easily to compute is a K-invariant of the Postnikov tower, and I have product used for define Quinlan model on different graded algebra. So this thing. Then the next thing is a kind of improvement is a Hunterian star shapes. That now he not only consider different grade commutative algebra, but he consider finite. Finite is a better. And then in later paper, that is in 1917 and in about 2008 or something like that, he wrote a paper, Schlesinger, in archive, that very widely cited but never published. And then he says that's how to reconsider that Hunterian star-shaped model. That is actually that it is first you consider Tata Iosophic resolution of the commutative algebra cohomology. So, but now hyperturb is so that the differential encode that D from Sullivan model. Now that it becomes that how to deformation theory. Yeah. So every repetition give a different homotopy type, and using filtration he try to get. But in this sense, how to say? in sense that the paper is formally very interesting because of deformation theory, but he has a very hard group action, and he wrote that to understand the homotopy type, how to say, complex set of the invariant homotopy type is a complex set invariant of the action of a very bigly group on search space. And as I'm working with a kind of classification of these orbits, usually cannot classify unless a very some specific dimension or degree. Yeah. So that he says that's impossible to compute the complex set of invariant.
Sorry, one. So L equals 2 as inverse on this formula. Is it a Freely algebra? What is this? In the Quillian module, L equals 2.
The Quillian.
Yeah.
Quillian is a differential. Yes. Yes, differential directly algebra, and the homology of it is you compute the homology of the and L here is a Freely algebra. You take the suspension exactly. Yeah. Of this. So that's a Quillian model. Actually, that's like in homology theory. If you begin from the homology or the homotopy groups, everything very simple, but computation is not easy. If you begin from cohomology, that is a little bit harder to define, but the structure is much richer. So that is a Sullivan later model is more popular. Of course, there's a several paper discussing the relation between Sullivan model and Quillian theorem, and notable is a Berkelund paper. But they also consider under certain restriction. So that is mainly 3, and then enter another paper. I somehow have my intuition that's very interesting about the 3 years ago. So that's a Kadeshvili Minimansian model that is using homotopy transfer. Yeah. Then he considers that then you put every information on the cohomology algebra and higher operation. And transfer this to cohomology, and see the M1 equals 0, so that's M2 equals the operation in algebra. So everything encode from M3. Yeah. So that many people like even how to say Martin Morgan wrote that's how this M3 related to massive product, and K under the another. Of course, you have to normalize things, and you got a relation. Yes, that is not completely 3. And the one thing I think that's the thing interesting, but I think that's we still cannot classify that. I think out of 3 years ago, because that is only like a Sullivan model. You have the model. So how it proves that the two models are the same? You have to define isomorphism. How to define it? Of course, now it has an algorithm. But algorithm is a kind of computer science. Yeah, you can do something, but not theory. The same here for Kadeshvili model. So you say that everything is a unique net up to isotopy. Yes, that's you have the model, but the another model, they are the same or not, you have to define. Yeah? So like Schlesinger and Starship, they say that they have space define module equivalent, and module equivalent is a very group action, bigger action. On these things that you anyway you have to define modulo action. And I see that how to define action. Some people somehow that kind of they define some in some cases they can say that's equivalent locally, but somehow they never try to think further, yeah, because it takes some computation, and then thanks to experimental possibility, it is AI. I experimented, and then somehow I got it, yeah. But of course, before this question, I thought about 3 years ago. You already work 5 years, 7 years, 6 years ago on another problem. That is now I should talk about it. But Hodge homotopy and minimal Unital Cyclic C infinity algebra. So first, we consider only closed manifold orientable. And let's say oriented. So it fix some orientation. Yeah. So orientation is nothing else as a fundamental class, right? And for fundamental class, you can define the pairing in the cohomology. So the question that's how you extend this pairing on differential graded algebra. Of course, you can define in this way, but this pairing is very degenerated, right? And degenerated, then how we do it? So that's one of the our paper is Kawai, Fiorenza, and Schwachhöfer 6 years ago, but published only 5 years ago. Yeah, that is it has a very simple algorithm to make it non-degenerated. So that's first, of course, formulated in our paper is Fiorenza-Kawai-Lê-Schwachhöfer. And then after 2 years, you understand how formulated it a little bit better, but the same idea, yeah. So you consider you already know that you have some differential graded algebra. And you call that Poincare because the cohomology is a Poincare algebra. You can leave it, but pairing is possibly degenerated. And then you define, nevertheless, Hodge homotopy is actually, I wanted to give a talk after this paper, right? The minus of degree -1 look like in the Hodge case, but a little bit, it's a bit, how to say, you have harmonic subspace, everything like that, the composition like a Hodge case, but the operator D minus here is not D star, but the composition of D star is green operator. And that's very interesting for analysis because a green operator, inverse operator is, yeah. So then you have the quasi-amorphism. So this thing already know Merkulov, he used it, but he consider only case dram algebras, and you try to mimic, but he never write, how to say, what is the better, he never write on this requirement. That's only the requirement, that's he write it, yeah, that's only the commutative relation, and you can define a lot of these commutative relation on even finite differential graded algebra. But that's we first time define it. And then you have the theorem that the transfer minimal C infinity algebra is a unital and cyclic. So yeah, what doesn't mean unital? Unital, that means that look like you have some operator algebra, but I didn't write here. So unitant, of course, that's how you consider this unitant. It's M1, M2, M1 must be the trivial. M2 is like is a commutative algebra. High operation, it puts the unitant, it equals 0. So every time you have some unitant in the high operation, vanish. Yeah, that's a terribly good, simplify many computation. And cyclic, that means invariant under cyclic permutation. And that already noted by Gonsiewicz, and he considered, yeah, thing before. So that's...
He wrote about that.
Yeah, and the Unitan also wrote in the Gessler and paper, is his student. So that also because I remember when before he wrote the paper, it's Fiorenza 2 years ago, and it struggled with some computations. So I noticed that some identity, it got very it's a lot of work can be driven if you apply unitality. Yeah. Then that unitality simplify a lot of things. Now cyclic you get also thing. But the more than that, you notice is the thing. That's if you consider transferred C infinity algebra on using our Hodge operator, you have more symmetry. And this is a symmetry, you call that generalized asymmetry and generalized even symmetry. So asymmetry is that what is thing here? That first, of course, you got in the case only x and y x, and there are lot ez and ez, yeah. And then I try to think that what happened if you have some more variable, then you can only get these things. So of course you can get more symmetry, but that is sufficient for our application in this paper. And that kind of, you have a lot of symmetry. So that even symmetry. And this symmetry is very beautiful because I shall show you later. Yes, so the another kind of symmetry is that you need it to cancellating several computation later. So now I say that I consider both cases, rational and real homotopy. Real homotopy, everybody knows that's a theorem algebra, yeah, and that is an example of the overcool is the reason by how to come Lambrecht-Stanley and Chilibas Fukaya-Lachep. Yes, that's a Lambrecht-Stanley says that they can get some finite model, finite dimensional model of the differential grade algebra overcool. But then Chilibas Fukaya applies some kind of a Hodge homotopy operator like us, yeah. But they did not get the same name because they did rely on this requirement for operator. But actually, they apply the same technology, and then they can quotient out the kernel. If the dimension is a finite, it can quotient out somehow kernel. Only half is the infinite, yeah. But once you have finite and you quotient out the kernel, then you get the non-degenerated differential gradient algebra and encode the same information. So now I go to main part of the my talk today and the main idea. So on this idea is already previously noted up to some technical lemma. So the main idea is isotopy modulo. So first you thinking like a isotopy modulo equivalent up to kz, yeah, a function. So that's first it defines that two structures are equal modulo if they ME are equal. That's easy. That's many people consider. Once you have the ME equal, and the next step is different how you think that they are equal or not. Yeah. So I think that's why you cannot ask another question. They are not equal, but equivalent. So that is thing is equivalent if there exists some infinity, say infinity isotopy. That infinity isotopy, that means that the first term is the only identity. So such that after apply this isotopy, you got equality. Yeah, so isotopy modulo, if there exists topy modulo, then apply to it, then they are equal modulo. Yeah, so first that is not obvious that it define equivalent relation or not. So I try to use also AI to compute a lot of relation, and they really define equivalent relation. But then you have the very simple proof. But at least that also so good thing. Sorry. Yes, so that's why you need to consider that's a very complicated multiplication of C infinity isotopy he consider DGLA. So thing is, as you maybe remember, that I say that I interested about 3 years ago on this equivalent relation and try to check a lot of paper. And then Kadeshvili wrote a lot about the testing modern Gestenhaber homotopy algebra, a lot of operation. But from this, a lot of operations, the most important thing is Gestenhaber differential graded Lie algebra. So I say that I have this thing because if you write definition of this operator of the define what is the differential graded Lie algebra of the Gestenhaber, that is more than one page on the research paper, so there's no time to write it. But the idea is that how to say on this there are a lot of operation in the you have a lot of MK operation, yes, but then you can define homotopy Gestenhaber algebra, but you need to know kind of dressing it in less information. That is a differential graded Lie algebra.
Sorry, Juan, how is this filtration constructed?
Filtration constructed by the arity. How many variables? You consider Hodge cochain complex, right? Then you have degree of the operator and the arity. So only arity is a filtration. That three form, 4 form, yeah. So that's a filtration. So
this slide. So I just want to understand. So you give 2 definitions here: this equality modulo K, and then isotopy modulo K. And you're saying these relations are the same?
No, I say that's a isotopy modulo K. When first I introduce, I don't know it's the equivalent relation. If A and
so the claim is isotopy modulo K is an equivalence relation.
Yeah.
Okay.
So I need to prove it, and the first proof using the C-infinity algebra quite long. Okay. And then I say that, but there are very simple proofs that are only 2 lines. But the 2 lines is
But sorry. So what? And what is the role of the first definition?
The first definition, because only isotopy modulo K, actually the pen look like a K, that means phi of A1 is equal modulo K E2.
Yeah, but where would you use this equality modulo K?
Yeah, so that's a pen, of course, here, that because how to say, the thing is the following. A1, K, A2, if exists of isotopy, just that phi A1 equal modulo K A2 modulo K. So this is first definition. They are equal modulo K if the first K term is equal. But isotopy already you have to apply some isotopy.
Oh, I see. Okay, just to state definition of isotopy, you need okay. So this tilde K is the first definition. Okay.
How to say? Not precise language. Yeah. But
no.
That is
Paints. Okay, so paints is reduces to this.
Yeah, that's
equality. Yeah.
So what is different from other people? They already consider that I mean that on this Starship-Schlesinger, they consider that phi1 equal. Yeah, and that is a classification problem, group action. Yeah, and then they ask what's the invariant of group action, that you know that you cannot answer even in Lie algebra except for few cases.
Is this related to the filtration on the next page?
Yes.
Oh, okay.
Yeah, so I say that's the first we try to prove using on this terrible language of the infinite algebra. But then, of course, thanks to on this AI, somehow I come to realize that you can use the differential graded Lie algebra. So, but the only thing that you need to write definition of the different, I say that's very long. But the people not did knew it. That is Gestenhaber in the Voronov wrote a paper, first paper already 95. And Kadeshvili wrote 3 papers.
You said Voronov, Sasha Voronov?
Yes. The 3 papers. How is Tristan Haber? But he considered not only this year. He also say that the structure of the Tristan-Haber differential Cavalcanti algebra is sitting inside of the Tristan-Haber homotopy algebra. That means you have more operation. And the first thing is that a lot of operation, how you can filter, what is the most important. So if you filter only differential Cavalcanti algebra is much simpler, yeah. So that's first, I also kind of frightened because this Tristan-Haber homotopy algebra. But yeah, once you know what the extension information, that is simpler. So extension information is only Tristan-Haber differential algebra inside this homotopy algebra. So I see that as this important thing because the filtration is a pro-nilpotent. So it converts everything. Once then it's the orbit modulus k is a filtration up to k time. So that defines the equivalent relation immediately. So that's if you use the Rangnick-Lickerated algebra, once you know equivalent, then everything trivial. That I try to prove using only C infinity isotopy, yeah, computation, terribly hard, yeah. But of course, this theorem first I prove is a graded Lie algebra. The first theorem I just two space I see infinite isomorphic if and only the isotopic modulus k for on k that can be proved using directly language of C infinity algebra. But using DG algebra, it's actually few lines. And here's a few pages, yeah. So and then now the next things are so that's try to compute what is obstruction, yeah. So that first, of course, I already know that's not, but somehow it can be easy to know that's a primary obstruction to C infinite such a equivalent module 3 if and only list that first obstruction class, that is cohomology class of the M3 in the Harrison cohomology, yeah, the equal to 3, and that somehow you know because he already work out this thing, but a little bit different. But the first prime in the paper, previous paper is Domenico. But this thing is interesting now, Sasha, the cyclic case, because it uses transformation proposed by Lode. You can move this class to the cyclic cohomology. Yeah. And then the next thing, so the secondary obstruction theory, and that is actually Domenico only done the one. I have the idea of obstruction theory, but Domenico says that you cannot get anything canonical. Once you think that you know everything, then you don't want to do. Yeah, I didn't know everything, so I try to do. So so that's now the next thing. That's if M3 is equal, that then I assume that's the next question. If A1 equal 3, then what when they for equal 2, really? When each condition, yeah. So you can write down abstraction class, and that is a very nice. Very nice, write down completely, but also complication a little bit heavy. So I don't want to write, but only explain geometry. The geometry here is a little bit different because in general abstraction theory you have only one class. But here my abstraction is affine space, and this I have attached affine space. And this affine space is a linear space if and only if they are equal modulus 0. So that means affine space contains 0 point. Yeah. So that is already interesting. And then now how to provide the General case. General case, you can do the same thing, and much interestingly that you also have alpha space. So the picture is like that. Yeah, you consider the space of the here space of say infinity, not only structure but the enhancements. Enhancements, that means you have only the m1 equal 0, m2 equal m2 of the multiplication of cohomology algebra. So what is important? Only m3. Yeah, so that's the first operator is a fixed. So this space, then you ask if you thinking like a Schlesinger and Starship, and many people also doing before me, because actually I do is for deformation on general filter differential gradedly algebra, and that only considered by people before. Gunderman means so that's actually my theorem. I work for general theorem differential gradedly algebra. So that first I say that if they are equal model 3, then the abstraction class M3. Yeah. So define X on X, because that's an equivalent model case. Therefore, you have stratification here. Yeah. So now you know that on X stratification, you ask model 3 equal that's the equivalent model 3. Yeah. Then it's also like a stratification again, and defined by affine space. So that's locally you can define. What is interesting here? That's locally you can define absolute invariant, because an affine space you can never fix original. But once you fix it, the another thing is like a linear space. Yeah. So it look like a but you don't know what is the kind of the good original, except the case it is a Forman space. Forman space is and everything ends equal 0. Yeah, then you can fix it. But on another class where the canonical, you don't know, but you have the kind of affine structure stratification on each part. So it is a kind of the more generalization of the classical abstraction theory. So I also do not describe on this theory, and that is on this computation, very interesting. Also applied by, how to say, Baker Campaign Hausdorff formula computation. So now apply to it, then you got the finite classification following. For dimension R minus one connected manifold of dimension less than something L here. Also, if it's R, that means connected type, you can increase L. So that's L is the first minimum model number such that equilibrium, right? So that's you increase L. So that's takes a smallest number L. And you say that's a rational or real homotopy type defined uniquely by cohomology here and the isotopy module L minus 2. So you try to apply L minus 2 step, you stop, and you have the stratification on here. So finiting. So
equal to L. How did you get this inequality for N?
Yeah, so for example, that is a low dimension case. That is the L equal for example, that if you have the 3-dimension N equal R3, then N equal 1. N equal 6N plus 4, I think so, N equal 2, something like that. Every time you take a minus 3, let me 3. Even I confuse plus minus, but it's very easy. Error equal 2. Here that is 7. Error equal 2. Here equal 8. So that are correct. Yeah. So that 7 dimensions, then you need only one class, how to say, character class. So that is master class. They call it Bianchi master class, and Bianchi master class in dimension 7 classify homotopy type. In dimension 8, the except master class, you need some guys. That means not some guy. My very nice colleague, Johannes-Nordström, he gave a talk in our seminar. And then he worked on dimension 8. He find something like on the except the pentagon. But the day I upload my paper on ASCR, he sent me the revised version. Computation on the, how to say, on the representation theorem, 20 pages compute a different thing. And I only try to prove some person better.
Also used AI.
No. I think that's I don't know, but that is a yes. They use a kind of classic Sullivan theorem and representation theory try to figure out. Yeah. But here I guess the kind of filter differentiation gradient wants everything. Yeah. So so then so every time plus 1 then minus 1. Yeah. Error minus 1 error go this way. Then next pages. Yeah, so I already see. This is error minus 2 is a format. It already proved by Miller using Quinlan theory, and quite complicated here. Check online proof, yeah. And then here. So now it turns the infinite Solution model into finite set commutative classes. So look very simple thing. Next, now I should say about the our work with Domenico Fiorenza. Actually, that's Domenico Fiorenza has some external circumstances, so that he could not. I visit him in September, and that time he already has some problem, but that thing became kind of urgent, and then in October, November, December, he could not work, yeah. And then somehow it's on the AI work very quickly. So he refused to be co-author. I say, Domenico, he contribute a lot important idea. No, I had only 1, 2, 3. So that is in Srini, I still put here, but now he strictly, yeah. So actually that is the theorem you only want to prove long time ago, and that is how to say. This theorem is the following thing. Cavalcanti in 2006 already proved the version is the following thing. You consider R minus 1 cognitive manifold of degree for R minus 1 and B less than equal to. So you remember, so that's a Miller. What is the proof the previous? Miller that B minus 2, that's a 1 dimension less than Foreman. So he asks, if you increase dimension, what happened? So Cavalcanti says that, okay, you increase dimension 1, but you put 2 extra conditions. First, that's the first Betty number is less than or equal to 3. Second thing, you have left set element. Yeah, left set element. Then he still gets the formality. He proved it, but the formality, no, he did not prove formality. He proves that on Marseille operation vanished. Then, of course, on Marseille operation vanish is not the same as the formality, right? So then Crowley-Nordström says that not only on Marseille operation vanish, but the formality and the intrinsic formality. The intrinsic not depend only on cohomology algebra and not on on the differential concrete differential graded algebra. Yeah, and as it proved, in general, how to say, we cannot check every argument in Nordström and Crowley paper, and some theorems that some theorem even Domenico amplify counterexample. Yeah, so that's because of the language they use, the Sullivan model, and a lot of the representation theory quotient out some things and things. So that's very hard. But nevertheless, the theorem is proved. You have the new proof of it, and the new proof of it is very nice. Yes, very nice. That is the following thing. So first, we consider that because have left set properties and consider inverse of the left set operator. Yeah, so then you have this operator denoted by R. Then what you do next is, of course, you consider symmetry of the operator. Symmetry operator. So let me check, show you the thing. Here, you notice that our operator is sharp, E on Z here, and Z on E. So you change EZ operation, yeah? Why you change it? Of course, that's you already knew the paper by Crowley-Nordström, that's the Massey-Bianchi tensor is somehow related to Ricci tensor. So you try to see that's what kind of symmetry of our operation. Then you switch it and you got it. So that you got it. Only for the case R is even, then tensor satisfies that exactly symmetry of the Riemannian curvature tensor. That is once you know it, then you check it so that you know how. And then now the dimension y should be less than equal less than equal 3. In this case, it satisfies Bianchi identity, so algebraic curvature tensor representation theory in low dimension. If the odd, you have the linear operator here. Yeah. So first, Bianchi identity is not just a geometric miracle, it's a geometric shadow of symphony relation because it uses how to say, Schulten, vanishing, Harrison change, yeah, and something you also got it in the case of R even, you get Bianchi identity. So once you got my identity outline of new proof, that's our proof is a Domenico. So if the R even, so in this case, R defined uniquely by Ricci tensor. So that instead the tensor in 4 degree now is lower degree to trace of Ricci tensor. And you define Ricci tensor again, you know, so from Riemann geometry, you have the scalar curvature traceless part of it. Using this decomposition generalized symmetry, then you can find a cosine. That means that this equation, after decomposition, you can solve it. Not very hard. It's now, yeah, not very hard, yes, but it also consumes AI a bit, yeah. But in principle, the main idea is a Ricci tensor decomposition. So that's in this case, we only know that from our theorem. That's in that dimension, then you need to compute only one obstruction class. If the equal, then it's isotopy. That is a theorem. Yeah, but this theorem also, I say that my finite-type theorem only in this case proved by Crowley and Nordström, but the other case not yet. Yeah. So if R ought to prove, so that's to prove is you same proof because you already know how symmetry, but you have to distinguish odd and even. You work on this graded theory. You know that a little bit different, but somehow you can figure out. Yeah. And but actually, you have already another proof. You did it with the Domenico 3 years ago. Then you leave it away because you cannot do anything else more. because that time you did not use cyclicity. Only now you discover cyclicity. But in that case, that's I already told you that you have a very good algorithm. It's Fiorenza-Kawai and Lorentz-Schwachhöfer. That's from the DRAM algebra or any Poincare differential algebra. You make the finite dimension non-linear algebra and have the canonical form of this algebra. And this algebra says that in the case of the different odd, yes, you compute a little bit the condition of our theorem give immediately that is the condition that is a formality. So this theorem says kind of shows the power of the Hodge homotopy theory, and very short. Now, in the last 10 minutes, I should say about the extension of Cavalcanti formality result. Now, for Cavalcanti, also consider the case of the 4K. So let me tell you what's the Cavalcanti. So Miller says that 4K minus 2 is a formal. So Cavalcanti, as what happened is 4K minus 1 and 4K, yeah? So 4K minus 1 is exactly what I did just show you. Yes, that's in this case, you put the condition. So Cavalcanti says that he puts a left set operator invariant, yes, but he also puts a condition B error less than equal to 3 for 4K minus 1 and for 4K he puts a condition for error B error less than equal to 2. Because every time you increase dimension, you have to put more constraint. So that is then I think that's how I try to generalize this. So I generalize first. I put the dimension not only for error minus 1, but phi error minus 2. So find the condition. Then first I guess the condition that the algebra is a quasi isomorphic to minimal Unital Cyclic algebra very niche for K bigger than equal 4. So that means these algebra defined uniquely by primary abstraction class. But the second statement is exactly that's the Cavalcanti. So if it's a 4 error, then A star is a formal. So I check that the second statement is a Cavalcanti, but a new proof using Hodge homotopy. Yeah. So the proofs, how to say, first entity is again that's if the phi r minus 3, then it's satisfy without even left set condition. So it increase dimension one more. Then you ask push much more condition, better number and left set isomorphism. Then you get the same thing like a dimension lower, yeah. So therefore, that's to prove it, you need to only to consider the case phi r minus 2 under the left set condition. And then using on this generalized symmetric cyclicity intellectually, you just write a lot of the equation, and somehow you conclude that m for equal 0. So that is not very hard, kind of combinatorial checking. But the next thing is a little bit harder because solving some cohomological algebra equation. 5 phi subset and 3 equal d phi, yeah. And then you need to solve the equation and prove that I told you over-determined equation, how is the exists, so that compatibility condition, so that yes, somehow you can prove it. And now apply finite-type theorem if the n4 vanish, and 3 is a cohomology class equal 0 by finite-type theorem, then it's a formal. You need only to computize, yeah? So that is a main part. So now is a kind of final remark. So so that is how to say. First, that's what's a really new point here. So instead to consider the Gaussian space by group action, I consider stratification and the concept of isotopy. Yeah, so that is incredibly it works. Yeah. So and then it works because not by algorithm, by using filter differential graded Lie algebra. And then how to say, we already proved in our previous work with Domenico that the Harrison cohomology class is the same. That means define uniquely Bianchi Massey tensor Crowley-Nordström. And then I say that in later works that Nagy and Nordström try to increase for dimension 8. They even 6R minus 4. He tried to find some the second absolute invariant, and so that is class 5. So that's very complicated work. And then because my abstraction is like a stratified alpha space. So in principle, from stratified alpha space, if you choose a correct original, you can define how to say global, absolute invariant. Yeah, but and therefore that's a Nagy Nordström invariant should be expressed in this term, but I don't know how to express it. And then, yes, so now I consider back to Schlesinger-Stashev point of view. He already used differential graded Lie algebra, deformation theory, but he also considered filtration, but he didn't not go further, yeah. So he stopped at there, and then he cannot define homotopy invariant. And then also related to something like a Chilibach, Hayek, and Vonko, because he's a guy also use the same assets like Hodge homotopy and homotopy transfer. They consider Unital Cyclic homology algebra, but working in the sense of the string topology and how to IBL infinity structure. Yeah, so. I think that's our technique can be applied to their work. But let's say do it. I should not do, yeah. So that's another conjecture, because the first, of course, that's the extension of Cavalcanti paper. I only put to easiest case phi r minus 2, because the first non-trivial dimension after phi r minus 3. But if you consider another work, then the next dimension should be not phi r minus 2, but 6r minus 4, yeah. So that is a thin conjecture. I don't know how to prove it. Could be good problem for student. Okay, then what answer? Of course, you can try to use it technology and the idea to and the finity algebra of automorphism group of X, yeah. So that means that's a mapping space, mode infinity mapping space. So I have looked at it, seem mainly similar and kind of can be done. And here's finally here's a paper address of my paper. So thank you.
Thank you for the interesting talk. Some questions online? Okay, maybe if no one is asking, maybe I have two. Yes. One is very naive. So if I understand correctly, your main focus was on infinity algebra related to algebraic topology, right? Because they arise from rational homotopy theory. But how much more general is this concept? You can study this by...
the kind of classification theory, I make the theory for affine structure. Everything works for finite differential greatly algebra.
It's more general than
yes.
just rational.
Also the theory of the abstract class, because of many deformation theory, you know that Morey-Cartan equation. So I also start from Morey-Cartan equation for differential greatly algebra, but assume that finite nilpotent, pro-nilpotent algebra.
Previous slide of you when you mentioned this, the mapping space from X to X, right? So can you comment on this a bit, or it's too early?
Yeah.
Yes, about that.
And I checked. Too early. So that is yes. That I just start to think about it. Yeah. So I didn't want to say too early.
And maybe 4, also 2 slides before, right? 4, 5 and 4. Okay, so about this infinity algebras related to configuration space integrals. Yeah. Is it? It's not your result. Is it easy to understand how is it related, or?
So actually that's a very interesting. That Pavel Hayek, I met him in the SNE conference 6 years ago before, and I talked to him, and that's through him I learned that our work also. You remember that's the first I think about real homotopy, but rational homotopy also work because. After discussion is him, but he also wrote that he marked in some his paper, but that's not very big deal. Yeah, so and then he also used a lot of our ideas. That our main idea that time to construct some canonical finite dimensional space that you call that small quotient algebra in their work. So that if you read their work, they thank me, but actually only Pavel Hayek talked to me. Yeah, so. So that is why there are a lot of the intersection, because talk to each other, use some idea in early stage, but they apply to string topology, and that I didn't know, and of course there is a much more advanced. Once they knew this idea, they figure out immediately how to improve. So I don't want to.
That Hayek is invited to give a talk at our seminar.
But Pavel Hayek, I invited him to give a talk on the 20 May. That is yeah, and then he from the Wolfram group. So that's a great guy.
Yeah, would be interesting. Okay. Other questions or comments? Okay. Okay. Igor.
No. I think there's a possible question, but now I don't see any questions. So yeah, I think we can thank Van again. Yeah.
So thank you for.